No, white chalk. Oh, this is white. Okay. Okay, thanks. Are there questions? Yes. Physical significance. Well, it's just there, meaning you cannot. It basically say, yeah, I mean, the extra term is essentially signifying that Gij, the first derivative of Gij cannot be it.
Means that when you write the derivative, is the old derivative with the transformation addition term of involves the Gij, not the derivative.
Exactly, yeah. So this extra term is something that is not part of the tensor transformation laws, right? Because in the tensor transformation law, the transformation of a tensor should be tensor multiplied by some products, right? And that's what fails when you take the first derivative. Any other question? Yes. How? Yeah, we'll do that today, right? How to calculate the variation, right? We'll calculate the first variation and try to set it to 0 to find the equation for the curve. Yes, indeed, because the length of a curve, right, by definition, is coordinate independent, right? Because that's how you in fact define the transformation law of Gij, right? Because we said that the length is fixed, right? And so Gij transforms so as to keep the length fixed, right? So indeed, length of the curve should be independent of the transfer coordinate system. Any other question? Okay, so let me write down the length of the curve that we had written down last time. So if we take a curve C, right, say between say 2 points A and B, we had written down the expression for the length as integral over C ds, okay, but then we wrote it also in the parametric form, 0 to 1 du. With the condition that x at u equal to 0 corresponds to the coordinates of the point A, and x at u equal to 1 corresponds to the coordinate of the point B. Okay. And this expression, you can easily verify that if you change u to some other variable v, which is a function of u, okay, this expression is invariant, right? Because if you change, say, suppose u is f of v, right? Then this will become f prime of v dv, okay? And then ddu will bring down 1 over f prime of v, okay? And those cancel. Okay, so this is independent of how you parameterize, which is as it should be, because this is the original expression had no knowledge of how you parameterize the curve. Well, you have to change u to f of v so that f of 0 is 0 and f of 1 is 1, right? So that by construction you don't let the limits change. Otherwise, you have to put a defined limits. Okay, so the idea is that we will try to find the equation for the geodesic, right? This is of course for any curve, right? This is not necessarily for geodesic, but the geodesics have the property that when you take the variation, if you take a different curve with the same endpoints, then the length of the curve shouldn't change in first order in the variation. Okay, that's the meaning of the curve being an extremum. Okay, of the length of the curve being an extremum. So to do that, let's try to calculate delta L. Yes, it can be maximum, right? Yeah, so we will not demand that it's a minimum, right? And the reason is that, I mean, we in curved space, right, there are, I mean, natural definition of geodesic, which actually is a local maximum, right? If you take a sphere with 2 points on the sphere, okay, then you have some idea of what the geodesic is, right? You go along a great circle, right, from one point to the other, but you can also go along a great circle in the other direction, right, which is also a geodesic, but which becomes a maximum, right, under local variation. So that's why we allow both maximum and minimum. Okay, we don't demand that it's a minimum necessarily. It need not, right? What I'm saying is the definition that we'll be using, right, as long as it extremizes, that's good enough. Okay, we will not require that the secondary variation is positive.
Is there a visual example where the minimum or maximum, I mean, like the other greater circle,
Greater
that's
circle.
also locally a minimum, right? If it's the three usual a square plus b square.
Yeah, I think in that case you can probably find a local variation which will reduce the length. Okay, I'm not completely sure, right? Once to check.
Yeah, that is, you can just shift the curves and that will just increase the.
Yeah, but local shift, I agree, right? Okay, yeah. There are okay. One has to think. I have to think to see if I can find an example where it actually local is a maximum. Yeah, it's possible, right? I mean, because but this is we are trying to define for general metric, right? Hyperbolic metric, for example, where it may happen that the local variation can reduce the length rather than increase it. Locally, it is possible. Okay, what I'm going to do, right? That equation for the geodesic will not use the fact that the second derivative is positive, right? So whatever geodesic equation will be deriving, that is valid for a local extremum, right? Now there may be a separate proof that local extremum, right, means local minimum, right? That we are not going to use right now. Okay, so delta L will be given by integral. You have to vary this, right? So we use basically chain rule. So Gij of x half okay, let me change the index here so that it doesn't get confused with the other index that I'll be using. Okay, so half should be outside. Yes, thank you. And then the variation of whatever is inside the square root. Okay. So let me write this. So delta Gij of x. I'm not writing the argument u, but x of course is a function of u. Okay, this two I have written because we have to vary this and this. Yeah, but by the symmetry of Gij, these two will give the same result, right? Whether to take the variation of this times this or this times the variation of that, right? The same result. That's why this factor of 2. And the variation is happening because the curve is changing, right? This you should keep in mind that x is changing to x plus delta x. So let's just try to expand this out, okay, and see what we get. So we'll just write down second line right now. So this gives you, the first one is given by derivative of Gij times delta xk. Okay, delta xk is the variation for a fixed u, right? This is the delta xk. This is delta x. Times dxi du dxj du, and then we have Gij of x times ddu of delta xi dxj du, 2 times. Okay, because this dxi du is varying simply because xi is going to xi plus delta xi. So idea is now that we will try to identify a coefficient of delta xk, right, and then use the fact that delta xk is arbitrary to set the coefficient to 0, right? That will be the geodesic equation. Okay. So for this term there is no problem, okay, but here you see that there is a ddu acting on delta x. Okay. So you have to somehow remove this ddu, okay, and that we will do by trying to do integration by parts, okay, because the boundary terms will vanish because delta x vanishes at the boundary. Okay, so you can try to do the integration by parts and put it on the rest of the terms in the expression.
We still have that factor, right?
Yes, yes, indeed, we have this factor. Okay, so you have to keep in mind. So when you do the integration by parts, okay, it will act on these, okay, but it will also act on this. Is clear? Okay. So that looks like a complicated expression, right? And you can of course go ahead and do this. Okay. But what we are going to do is to now follow a shortcut. Okay, and that is the following. So far, our choice of u has been completely arbitrary, right? We have not said anything about how we parameterize the curve. Okay. Now we are going to make a choice of how you parameterize the curve. Okay, we are not going to derive this for an arbitrary choice of parameter u, right? But only for a special class of choices of the parameter. Okay. And that choice of parameter, okay, is taken in such a way that equal interval in u gives equal length of the curve. Okay, imagine that we have taken this curve, right? The original curve. Yeah. We want to parameterize it by u, right? This is u equal to 0. This is u equal to 1. But what the value of u is here is up to us, right? Because you can choose anything between 0 and 1, right? As long as u increases monotonically as you move along the curve. So you can decide to choose u in such a way, okay, that as u changes by delta u, so suppose delta u here and delta u here, okay, same amount delta u, okay, that this segment and this segment has the same length. Is this clear? Right? In other words, we take the original curve, okay, that is a underlying metric. Okay, we just divide that original curve into n equal segments, okay, and call the first, you start at u equal to 0, right? Then the end of the first segment you declare as 1 over delta, 1 over n. End of the second segment you declare that corresponds to u equal to 2 over n. Next u equal to 3 over n, and so on. Is this point clear? Right? So we choose parameters. So we choose u such that equal interval in u gives equal length segment. Okay. So these are called affine parameters. Okay, because now we are not allowing an arbitrary choice of parameterization, we have a very specific choice, right? It's still not completely, yeah. So it's completely fixed once you demand that the total curve goes from 0 to 1. Okay, then you cannot even do any scaling. Okay. So you are going to derive the geodesic equation in this parameterization. Is this clear? Okay. So this means the ddu of square root gij of x dxi du dxj du equal to 0. But this is a length segment. Exactly. Yeah. This is like ds, right? So ds du. Yeah. So this is ds du. So d du of that should be 0.
We are choosing such a way that DSDU is a constant.
Exactly. So ds du is a constant along the curve. Yes. Divided by du. So that's dx du, ds du. Right?
That length should be
Yes, exactly. Right?
Then you should just divide by the whole square root divided by d.
Okay. See, length per unit. So u interval for length is fixed provided you fix the u interval, right? So for a given du, right, ds should be fixed. Right? ds by du should be not 0. If it's 0, then of course that means that as u is changing, there is no change in the length, right? So ds by du should be constant. Right? This is ds by du, right? This should be constant. So once you have chosen the parameter this way, right, then things become simple because now ddu acting on this gives you 0. Okay, so you don't have to worry about this anymore, right? So now the integration by parts becomes simple, right? We only have to worry about ddu acting on this. Okay. So this gives the geodesic equation in affine parameterization as the following. Minus it's clear. I just have integrated by parts this ddu. Right? There's an integral sitting outside. Okay. ddu acting on this doesn't do anything. Right? So this is as far as this is concerned, it's like a constant. Right? So ddu, when you integrate by parts, it basically is going to act on the rest of the product, which is here. Yes.
We are doing this trying to find some geodesic criteria, but since we are playing shortcuts, to limit the set we are picking this geodesic from, right?
No, it doesn't limit the geodesic because given any curve, we can always choose the parameter this way. It limits the choice of parameter, right? So the final formula that we are going to get, right, will not be invariant under an arbitrary change of parameters, right? But it doesn't limit the geodesic. Oh, because this was multiplied by this factor over here, right? So inside the integral, okay, I have substituted for the square bracket whatever appears here. Okay, and now I am doing ddu partial integration, right? So this is going to act on everything else which is there in the integrand, right? Which means the product of these two and the one that is outside, right? And now you are using the fact that on the outside the du doesn't act, right? It gives you 0. So that term you don't have to worry about. These just factors out as a constant, and then du acts on the rest. Is this manipulation clear? Okay. So now you are almost there. Okay. The only thing is that here you have xi, here you have xk. Right? So let's just change the labels. Okay, I'll just exchange I and k in this formula, right? Because those are summed over index anyway. Yeah, I and k are summed over index. So I'll write this as minus this one. I'm going to expand it out. Okay, this is the statement that the first order variation should vanish. Is this clear? So this, let me write it. Okay. So now delta xi can be dropped, right? This has to be true for every delta xi. So we can drop delta xi. Okay. And the other thing that we'll do is to multiply this by, so drop delta xi and multiply by G L I. Okay, L is a free index. Okay, I we are now going to contract, right? Because I was a, yeah. So once you have dropped delta xi, right, I becomes a free index. Okay. Now I can multiply by GLI. Okay. So what do we get? The first term is GLI minus and then minus. See here, this is the, I mean, the reason that I have multiplied by GLI, because it simplifies this, because GLI will give you delta LJ. Okay? G upper Li contractor, this will give you delta LJ. So that just becomes D2XL du square. Two times. Thank you. Is this clear? Okay. So now let's try to clean up this formula a bit. I'll just remove the 2 by multiplying by half and factor out and remove the minus sign. Okay. So multiply by minus half. We get see this term dxk du dxj du is the same. Okay. So 2 is and then minus okay, I wrote that last term first and then this one next, okay, and then this one. Now one more step is needed. You see, this product is symmetric under the exchange of J and K. Right? This is already symmetric under the exchange of J and K. Right? So we can leave it as it is. This one is not manifestly symmetric under the exchange of J and K, but we can manifestly symmetrize because it's multiply is something that is manifestly symmetric under exchange of J and K. Okay, the antisymmetric part will drop out anyway. So this one I can replace by okay, in the second term, I can just exchange J and K and exchange J and K here. Exchanging J and K here has no effect. Right? Then this will become the same as the first term, which will give you this. Is this clear? Okay, yeah. So let's suppose that we have Aij, sorry, Ajk. And A is an arbitrary matrix, not necessarily symmetric. Okay. I can write this as half Ajk dxj du dxk du plus in the other half, okay, this j and k are summed over here, right? So I can just exchange call j, k and kj. Okay. So in the other half, I get half akj dxk du dxj du. Okay, so that's the same as half of ajk plus akj dxj du dxk du. Right, so whenever it's multiplying some symmetric object, right, and all the indices are summed over, I can replace ajk by half of ajk plus akg, right? And that's all we have done here. This I have written as half of this plus this. Yes. How is it dropped here? Drop this delta xi. Basically, just remove delta xi because this is supposed to be true for all delta xi, right? Okay. So I can, whatever multiplies delta xi, I can set equal to 0. Okay. Yes. Okay, let me put it that way. Delta xi is completely up to us, right? Okay, so I can choose delta xi, choose delta xi as epsilon gli for any L. I can do that, right? Then you can forget about this line, right? I go directly from here to here, multiply by epsilon. Okay, and epsilon is completely arbitrary, so the coefficient has to vanish, right? That's what this equation is. Oh, because last term had GLI Gij. Yeah, GLI, right? I've taken this to be GLI. So I, when you sum, it gives you delta Lj. Okay. Delta Lj multiplies d2xj du square, right? So when you sum over j, only the j equal to L term contributes, right? So you get d2xl du square. Exactly. That's why I chose L to be a free index. Is this manipulation clear? Okay, I think once it happens several times, you'll get used to it, right? But initially it may look a little strange. So whenever there is a delta for chronicle delta, right? Sum over one of the indices basically means that wherever else that other index appears, you set it equal to the free index. Okay, that's why delta Li times, delta Lj times d2xj du square is thus d2xl du square, right? Because when you sum over j, only the j equal to L term is picked up. Is clear?
Essentially, we are removing chronicle delta and changing the index.
Exactly. I'm dropping the chronicle delta and changing the index j to L. So let me write that formula here. So there what I have used. So the manipulations are that we have G Li G Ij d2 xj square. So this is, so first this product becomes delta Lj chronicle delta because this product is an identity matrix, right? G upper Ij is the inverse of G times d2 xj square. So this is d2 xl d square. Okay, that's what I have used here. So this is clear. Now this expression, right, has a name, right? Remember what this expression is? That is the Christoffel symbol, right? Because let me write it out again. I think then it will become clear. So what the equation that we have gotten is d2xl u square plus half g li times so this thing that is in the square bracket multiplied by this half GLI, that is the Christoffel symbol. Okay, if you compare the expression for the Christoffel symbol that we had written, it's exactly that. So this means that we have the equation oh, this is the geodesic equation. Okay, in the affine parameter. Other questions? Would have gotten something else, yes. Would have gotten a more complicated version of the equation, right? Because the DDU of that thing will not appear. Okay. The fact that this is not valid in arbitrary parameterization, you can check, right? Suppose we now choose a different parameter v, e equal to some function of v, right? And try to write this equation in terms of v. Okay, you will find new terms in the equation, right? Because this part is reasonably simple, right? By chain rule, you convert ddu to ddu okay, with some f prime factor of f prime v. But this part has second derivative respect to u. Okay, so when you try to convert this to v, Yeah, you will get excess terms, right, which will not look like, which will not preserve this form. Okay. So this equation then is valid only in affine parameters, right, not in general. Okay. You can of course scale u, right? Scaling u means that instead of taking from 0 to 1, you could have taken from 0 to 2. Right? It makes no difference, right? So under scaling of u, this indeed is invariant, but not otherwise. Shifts as well, yes, indeed. Scaling as shifter, exactly. Yes.
Cases where we have to like take some other parameterization.
Yes. Are there cases? Yeah, I don't think there are cases, at least as long as the curve is smooth, you can always choose so that equal interval gives equal length. Right? It's up to us, right? We take the whole curve and just divide it into n parts, right? The way you take the limit, you divide it into n parts and then declare that the first corresponds to you going from 0 to 1 over n, second corresponds to 1 over n to 2 by n, and so on. And then at the end, you take n goes to infinity limit, right? That's what assigns u to every point on the curve. Yeah, it's also parameter of u, right? But it will change it only implicitly, right? Not explicitly. Value will not change, exactly, right? The what u corresponds to what x, that will change, right? But the value of the Christoffel symbol will not change. That is, at the same physical point, it will remain the same. If you choose a new set of coordinates, x, if you change x to x prime, yes, indeed, that it will change, right? So let me then make the statements, right, which will be, I'll not do this, but here it will be for you to verify. So exercise. Okay, so first exercise to check that ddu of gij of x we assume this to derive the geodesy equation, right? But now that you have derived the geodesy equation, we should be able to check that this is true, right? That the theory, the whole analysis is internally consistent. Okay? And this you can check because ddu you can easily calculate, right? One will come when ddu acts on this or this. Right? That will then that second derivative you can replace in terms of Christoffel symbol using this formula, right? And then ddu can also act on the u that is inside this. Yeah, that will give a derivative of g, and you have to check that the whole thing cancels at the end, and this combination is 0. For the geodesic, yes, exactly. Yeah, because you have derived the geodesic by assuming this, right? So it better be that after you have derived the equation, right, that this is consistent, right? That this indeed is constant along the geodesic. Is this clear? So this is the first exercise. The second exercise is to check that the form of the equation remains unchanged under coordinate transformation. Say xi equal to fi of x prime. So we go to a new coordinate system. Okay. The form of the equation shouldn't change. Okay. The reason that it shouldn't change is because when we derive this, okay, when we derive the geodesy equation, we didn't assume any particular choice of coordinate system, right? We derived it in any choice of coordinate system. So if things are consistent, it better be that after you have derived the equation, if you make a coordinate transformation, the form of the equation doesn't change. Is this clear? Right? So if you have these relations, say xi as a phi of x prime and x prime of I is the inverse a phi of x prime x. So for example, if you try to now calculate the second derivative of x prime I, it better follow from this, right? Calculate the second derivative of x prime I, but you have already calculated second derivative of x. You can express in terms of this, use this equation, sorry, not this equation, the geodesic equation. Okay. And you should be able to check that the second derivative of x prime I satisfies a similar equation with gamma replaced by gamma prime. Okay, there of course the coordinate transformation of gamma will be important. Right? The fact that gamma doesn't transform as a tensor, but there is an extra term will be needed to show that the form of the geodesic equation doesn't change under coordinate transformation.
So this will be some metric coordinates multiplied with coordinates.
Sorry, what's the question? No, maybe you go ahead first.
Yeah. So this first of all will involve some derivatives of the derivatives of coordinates. Extra term.
Exactly. So all those extra terms should cancel, will be absorbed into how gamma transforms. Was there a question on the Zoom? It was? Oh, I see. Okay. Is this okay? Are there questions? Yes. So suppose you have Euclidean geometry, the Christoffel symbol term becomes 0, and you get the equation of a straight line. Okay. But suppose the same straight line you want to write in the polar coordinates. Right? In the polar coordinate, this is not 0. Right? So the straight line written in the polar coordinate will satisfy this equation. Okay, with appropriate gamma calculated in the polar coordinates. Yeah, so this tells you how to write a straight line in the polar coordinates. Yes, meaning Riemannian versus Lorentzian. Yes, there.
Yeah, in case of Lorentz, like how will we deal with, because we can have negative ds, right?
Yeah, so we'll deal with them separately, the negative ds square and positive ds square.
So suppose there is a geodesic, I mean, somewhere it goes in, it has positive ds and somewhere.
That normally doesn't happen because ddu of ds, yeah, so that doesn't happen normally. Geodesics, if it starts from being time-like, right, it remains time-like. And if it starts from being space-like, it remains space-like. Yes, the ds du conservation, that's what I'm saying. The dds of ddu of, okay, this conservation, okay, you can say it's circular because you have assumed that it's possible to choose an affine parameter where this is constant, right? So that assumption then have to be justified. I mean, because you have assumed that to derive this. Okay? But generally, one can show that if you have a time start with the time-like geodesic, it remains time-like. How do you show that? Well, we can derive it in the general coordinate system, right? We didn't have to assume that dij, dxi, du, dxz, du equal to 0. Right? You can allow that to be non-zero. Right? Derive the more general geodesic equation, and based on that you can in a non-affine parameter. Right? And in that, using that equation, you can show that time-like geodesic doesn't become space-like. Otherwise, it will be very strange, right? Suppose an observer is moving in space-time, right? Moving along a time-like geodesic, and then suddenly you find that the geodesic has ended and becomes space-like. Right? That would be somewhat strange, but that doesn't happen, fortunately. Right? So you will continue to be time-like geodesic.
Then how do you parameterize null geodesic?
Yeah, so null geodesic, you can think of that as a special case. You cannot get it from the variational principle of this form, right? But you just define it as by this equation. Yeah, but u is there. ds is 0, but du need not be 0, right?
What is U in that? Yeah. Like what is the special affine parameter?
Some parameter along the geodesic.
So it will be independent of the parameter.
Exactly. It will be independent of ds. It will be independent of s because s never changes, right, along the null. So geodesics are the generalization of straight lines, right? And what we are asking is the generalization of the state time-like straight line versus space-like straight line versus null straight line, right? Time-like and space-like are okay because you can define it, because under small local variation, if you start with time-like, then infinitesimal variation will keep it time-like, and similarly for space-like. For null, you just take this as a definition of the geodesic.
No, but this will change under any you change U arbitrarily. This formula will change. In a time-like case, we didn't have because we didn't have choice on.
Yeah, so this formula, the point for null geodesic, you say there is some parameterization in which geodesic is this.
Some special parameter.
Exactly, right? But that parameter doesn't have the interpretation as the equal length is equal u, because length is always 0. Right? Change in length is always 0. So this interpretation is not there.
How is the equation of null case? Because we had the variation in L. We had something like dx dxi by d2 dxj by d2 gij the denominator.
Yeah. So for null geodesics, you don't derive it by using variational principle, right? What I'm saying, you just take this as a definition of a null geodesic. If it's the same for space, if the equation is the same for space-like and time-like, right, then null sits in between, right? So you declare that you will define null geodesics as this.
And what is that special? How is the special parameter there? Right? For a null geodesic, it seems that all parameters.
No, there is no special parameter defined there, right? You just say that it is, there is some parameter in which it is this. Yeah, so that definition is only for time-like and space-like. Okay, for null is the statement is that there is some parameterization in which the geodesic is this.
But then different people might come up with
No. Null geodesic, you will not come with define null geodesic, right? Because once you have said this, it defines a null geodesic, right? Let somebody else use a defined parameterization. The equation will be different. The curve will remain the same, right? So as long as there is one parameterization in which the equation looks like this, right, that is good enough to define null geodesic, right? I'm not giving any special meaning to that parameter, right? It is not that equal length means equal interval.
You mean to say that we have a second order differential equation here, right?
Yes.
So out of these sets of second order differential equations, in case of the Lorentzian metric, we have three classes of solutions.
Exactly.
One set will be time-like, one will be space-like.
Exactly. That's right. Exactly.
We are effectively treating null case as a limiting of.
Exactly. In between the time-like and space-like. Yes, maybe I'll say something, right? I mean, I don't know whether it will satisfy you, right? But I'll say something about this. Yes.
So then the point is that if you're in a, that's like interpreting the second term as some pseudo force, right? You're basically saying if you're in some rotating.
Yeah, okay. I mean, this is still Euclidean, completely Euclidean geometry, but it's okay. You can see it like a pseudo force in. If you had a mechanics problem, yes, okay,
Yeah,
go ahead. Yeah. Yeah.
Then you can interpret the second.
Exactly. So Newton's law in this coordinate system will not be that the second derivative is 0. Yeah.
So the second term is interpreted as some sort of force.
Okay, you can say that, yes.
So then what is this affine parameterization cover? Additional term that not affine parameterization. How do you interpret that?
That is just a parameterization, right? I mean, it need not be time, right? So I mean, you are thinking of u as a time. maybe it is true in some system, right? If u is time, then this is indeed. So if if you think of this as Newton's equation, you have in mind that u is being interpreted as a time, right? That's an additional data that comes from classical mechanics, right? That with that choice of time, it is this equation. So if you choose a different choice of time, then this equation will look different, right? Even Newton's equation, right? Take if t goes to f of t, it will get Newtons, right? Even if you don't change the spatial coordinate, because that f prime of t will enter when you take the second derivative, you will get a product of velocities. Yes.
Geodesics provide some
Two times meaning
first, like we find the geodesic in two different coordinate under two different coordinate transformation, then we do it once more to compare the curves.
no geodesic equation. The way you have derived it, it's valid in any coordinate system, right? And now you are saying that this equation is invariant under change of coordinate system, right? It better be, because we have not chosen any particular coordinate system to derive this, right? But nevertheless, once you have derived it, right, just to make sure that you have done everything correctly, you should check that when you make change of coordinates, it remains the same form, right? So when you look at, for example, the spherical polar coordinate and the Cartesian coordinate, the geodesic gives a straight line, as you understand, right? But the equation for a straight line in polar coordinates is different from that in the Cartesian coordinate, right? And that's what this second term is reflecting. If the two metrics are related by coordinate transformation, then they are by definition describing the same space, right? It's also you don't need geodesic for that, right? Two metrics related by coordinate transformation not describing the same space, right? And in that case, the geodesics will also be identical, right? Once you make the coordinate transformation, because geodesic is a property of the space, not the particular metric that you choose, not the particular coordinate system that you choose, right? So once you have chosen a space with a given metric, in all coordinates, geodesics will have the same form, right? Same physical, they are the same physical curves. Okay, are there questions? Okay, so let me now give some physical interpretation. Well, I don't know if I should call it physical interpretation, but at least some understanding. So now suppose you have a point x naught and you have a geodesic. That is okay, as long as it's extremum, it's geodesic. That's the definition. Yes. Yes. Well, it doesn't have to be minimal or maximal. It has to be extremal, right? And the definition of extremal is that the first derivative is zero. Doesn't matter even if all derivatives vanish, right? It's still okay. It's because you see, if suppose you have on a sphere, you have say north and south pole, right? And you have a geodesic connecting them, right? There is always a variation, okay, where the curve doesn't change at all, the length of the curve, because you just take there are many geodesics, right, connecting north and south pole, right? So if you vary the geodesic slowly along that direction, the length of the curve remains the same, right? So all variations will be 0. Okay? But doesn't matter, we'll still call that an extremal curve. Right? Each of these will be an extremal curve, and each of them will describe a geodesic.
So not all variations, right?
Not all variations,
Special kind of variation.
special kind of variation, right? But the way I've defined geodesic is that all variations will have first derivative 0, right? So similarly, you cannot demand that under all variations the second derivative is non-zero. Right? There are some variations where the second derivative is also 0. So that's not part of the definition of a geodesic, right? You as long as the first derivative is 0, it's good enough. Okay, so here the geodesic equation, this is the general geodesic equation. Okay. But if we choose a coordinate system, right? So we can choose a coordinate system. X prime such that this you have seen, right? It's always possible to choose a coordinate system in which you make the Christoffel symbol 0. In this case, let's look at how the geodesic looks like. So now the geodesic equation. So suppose u equal to u naught at x equal to x naught in the original system. Then in the new coordinate system, we have d2x prime L this one is of order u minus u naught. Why? Because this must vanish at x prime equal to x prime naught. That's the way I've chosen the coordinate system, right? It vanishes at x prime equal to x prime naught, which means it vanishes at u equal to u naught, right? Because u naught is the point where x prime reaches x prime naught in the geodesic. So it must be of order u minus u naught. Right? At a nearby point, it must be or higher. So now if you look at the solution, this implies that the solution near u naught, in general you would expect the solution will have a Taylor series expansion, right? The solution should have a Taylor series expansion. So how will it look? Say x prime I will be x prime I naught plus some ai plus higher order terms. But the claim is that this should be of order u minus u naught cube. Okay, let's see why. Right? Normally, you would expect the Taylor series expansion contains a u minus u naught square term, right? Okay, why is it of order that is? So u minus u naught square term is supposed to vanish. The reason is that if you substitute that solution here, the second derivative, if there is a term of order u minus u naught square, the second derivative will be non-zero at u equal to u naught. Right? But this one vanishes at u equal to u naught. Right? So if there is an order u minus u naught square term, then it would be inconsistent with this equation. Where the second derivative would be non-zero, right? But this term is 0. Right? So the sum of these two cannot be 0. Is this clear? So if we ignore this order u minus u naught cube term, you see that this is the equation for a straight line. That's clear. This is a parametric form of a straight line. So what this is saying is that the geodesics look like straight lines, okay, locally, near in the coordinate system in which the Christoffel symbol vanishes. So given a take any given point, right, and a curve and a geodesic passing through that point. So at that point, you can choose a coordinate system in which the Christoffel symbol vanishes, and in that coordinate system, the geodesics will look locally like a straight line. Yeah, that pick any point in space. Okay. So at that point, okay, there is a coordinate system in which the Christoffel symbol vanishes. So if you study the geodesic in that coordinate system, right, passing through that point, then locally around that point, the geodesic will look like a straight line. Right? To leading order, of course, right? Only the order u minus u naught square term is 0. It's not exactly a straight line because this term is absent. Right? But these are base you can do, right? So if you have a geodesic, you want to know how base can you make it look like a straight line. The point is that you have to go to a local coordinate system in which the Christoffel symbol vanishes, and in that coordinate system, the geodesic is as close to a straight line as you can get. Right, which means that you can make the second order term vanish. Is this clear? This term you cannot make vanish in general, right? Because the second derivative of gamma cannot always be made 0. Some components may be made 0, but we know that all components cannot be made 0 because the Riemann tensor is a tensor. Yes.
So it's Euclidean locally. I mean, it will look like a straight line geodesic.
Exactly, because the metric is locally Euclidean.
What happens when it goes over, like it fringes, or what happens? Exits the area where, or the patch where it is.
Oh, then in the original coordinate system, the geodesic starts curving, right? But then you can go to a new coordinate system in which again we can make the geodesic locally look like a straight line.
It's like you're on the surface of when you zoom enough, it becomes a straight line.
Exactly, that's right.
You zoom out, curves.
Exactly. Okay, so in this sense, geodesics are as close to a straight line as you can get. Okay, you cannot make it look exactly like a straight line, but it's as close to a straight line as you can get. Yes.
So this statement is general, right? We can always choose the coordinate system in this connection coefficient.
Yes.
And when we use this fact with the geodesic equation, we get that there will be no second order term.
Exactly. Right, so that's the sense in which it looks like a straight line.
Let's say in some other, I mean, somehow we get a second order.
Yes.
Then we wouldn't be able to say that it's a straight line. Because what the point is.
Well, see, locally, we can always say it's a straight line. It's a question of how close to a straight line you can get, right? So second order term means you are getting not getting that close to a straight line, right?
So how is that related to this? I mean, even if that would have been the case, we could have still called it a straight line.
But it's not as close to a straight line as you could get, right? So the local coordinate system, right, in which gamma is 0, is the base you can approach a straight line, right? Because in the second order term you can make it vanish. See, because in a Taylor series expansion, the leading term is always the first order term, right? That looks like a straight line, right? If you just throw everything else and keep the first order term, right? After all, I mean, locally, what can it happen, right? I mean, it just like geodesics will go out, right? Each of them look, if you go sufficiently small, it looks like a straight line. But this coordinate system has a feature that it makes it look like a straight line, okay, in a more non-trivial way. Okay, because even the second order term you are making vanish.
But if there is a second order term,
Yes.
let's say we calculate the second derivative of plus, then we have a leading order non-vanishing contribution.
Then yes, this is non-vanishing.
Yeah.
So it cannot be geodesic in this coordinate system.
So that means even if I go very close to the point see some kind of acceleration. So it's not a straight line.
Exactly, yeah. So if you have if you write a order u minus u naught square term, right, and you choose the coordinate system in which this is 0, right, then that is not a geodesic, right? You can of course draw a curve, right? Nobody can prevent you from drawing a curve through any point, right? Satisfy any equation, but it will not satisfy the geodesic equation. Yes.
You are writing
Xi is in terms of u, yes. Xi is in terms of yeah, because yeah, along a geodesic x is a function of u. Okay, so now I'm going to introduce another definition, the tangent vector and tangent space. So let's suppose that we have some point x naught. And we want to find a geodesic passing through x naught. So this means that we are trying to find a solution to the geodesic equation, right? D2 So this is a second order differential equation, right? L runs from 1 to n. So how many initial conditions do we need to solve a second order differential equation of this kind? 2n initial conditions, right? So we need 2n initial conditions. Okay, let's say u naught is the value of u at this point. So n of those initial conditions are fixed by the fact that x I at u naught should be equal to x naught I equal to 1 to n. Right? So this gives you n initial conditions. Is clear? Right? Because xi better be equal to x naught I. If it's passing through x naught, right, it better be equal to x naught I at u equal to u naught. The other n initial conditions come from the derivatives. So we need to specify an n component vector n1 n2 up to nn, which gives the first derivative of the xi at u naught. If you are given these two, we are done, right? We can solve the equations, right? So a geodesic is determined by this data. If we give the ni's and the x naught I, the geodesic is fixed. Is this clear? Now this in fact has a little redundant information, because if you have a parameterization by u, right, then any multiple of u is also a good affine parameter, because equal interval gives equal length. But that changing u to say lambda times u actually doesn't change the shape of the curve, right? So u and lambda u, right, actually describe the same geodesic. Okay, given a geodesy, you can just multiply u by lambda. It looks different function. Okay, instead of xi of lambda u, you will get xi of lambda u, but it's actually the same curve. So this means that this ni has somewhat redundant data. The overall coefficient, overall multiplicative constant in ni is irrelevant. Right? So ni and lambda ni gives same geodesy. Is that clear? Because by scaling u, you can change ni, but the scaling u doesn't change this equation. Right? You will solve the same equation with a different parameter. So you need an n-dimensional vector, but the overall normalization is not relevant. But let's just keep the overall normalization. Right now, let's not throw away the overall normalization, right? So you need an n-dimensional vector. So this vector is what is called a tangent vector to a geodesic at the point x naught. And if you are given this vector ni and the point where it's starting from, then the geodesic is fixed. Exactly. Once you specify the initial condition, right, then you don't need anything else, right? Then this differential equation takes over. Right? So only need the tangent vector at the point x naught. Okay, then the geodesic is fixed. The whole geodesic is fixed. Is this clear? It's like in flat space, right? If you have a point and if you are trying to describe a straight line passing through the point, you have to specify the slope, right? So in n-dimensional, how many slope parameters you do need to specify a straight line? N. Okay, it's n minus 1. In 2 dimensions, if you want to specify a straight line, right? What do you specify? You specify the origin, right? The x naught, but then you only have to specify one slope, right? dy dx, right? It looks like 2 because if you write the parametric form, y has some constant times u and x has some constant times u, right? It looks like 2 parameters, but only the ratio is important, right? If y equal to au and x equal to bu, then you eliminate u and write y equal to a over b times x, right? So that's the freedom of scaling u by lambda. Right? A and B individually you can change by scaling u by lambda, right? That's an irrelevant information. So it's the same as in flat space, right? The numbers haven't changed, right? In flat space, in n-dimensional flat space, you would have needed n minus 1 constants to specify the orientation of the geodesic, and that's also the case here. So n is what is called the tangent vector. And the vector space So in other words, the tangent space at x naught, okay, is a vector space, n-dimensional vector space. Given a vector in the tangent space gives a geodesic through x naught, and vice versa. Given a geodesic through x naught, describes a vector in the tangent space, up to this overall scaling by the lambda. So this is roughly gives the space of geodesics passing through x. Okay, given a vector in the tangent space, you can find a geodesic and vice versa. Now, I should warn you that these vectors are not the kind of vectors that you have introduced earlier, covariant and contravariant vectors, right? Because those covariant and contravariant vectors, right, are like things constructed out of a metric that is defined everywhere in space, right? And it has some particular coordinate transformation, right? Here, these are attached to geodesics, right? A tangent vector is attached to a specific point. And you can take any tangent vector, a particular tangent vector that gives a particular geodesic and vice versa. Okay? So even though I'm calling these vectors, right, you should not think of this as part of the tensors that we have introduced earlier, right? It's not those tensors. Okay? So a tangent vector is some particular property. So the tangent space is attached to a given point, and a vector in the tangent space corresponds to a particular geodesic passing through that point. Is that clear? Exactly. Earlier vectors are like fields, right? These are not like that. Nevertheless, we can ask that given n, right, how does it change under coordinate transformation? Suppose you have a particular geodesic in a particular coordinate system, right? That corresponds to a particular n. Now, I want to describe the same geodesic but in a different coordinate system. Right? How will it change? Okay, that's not very hard to find out. So n is dxi du, right, at x naught. That's the way I have defined. Why did I define? Yeah, that's the initial condition, right? dxi du is n. So this I can write okay. This one is the tangent vector in the new coordinate system. So this is so this factor is the same factor that would have gotten in the transformation of a vector field. Okay, of a covariant vector field. But nevertheless, these are not covariant vectors, sorry, contravariant vector field, but these are not contravariant vectors because these are not fields. Okay? These are not, it's not that they are defined, there are some objects defined everywhere in space. Okay, but this relation will nevertheless be used. Is this clear? So next thing we'll try to study, okay, let me just state the problem and then we'll do it tomorrow. Okay. So the next question that we're going to study is the following. Let's suppose in flat space, we are given two straight lines. We can decide if they are parallel or not. There is a well-defined notion of what you mean by two straight lines being parallel. Okay. Can we ask a similar question in chord space? Two geodesics at the parallel, if they don't intersect. Yeah, they don't intersect. Well, that's okay. You can call that the definition of parallel, but that's not quite the definition, right? Because in flat space, we are thinking of two dimensions. Indeed, two dimensions, two straight lines are parallel if they don't intersect. In three dimensions, I can draw two straight lines which don't intersect, but they are not parallel, right? One going like this, one going like this. Okay, so it's not a very good definition of that they don't intersect.
The last class we mentioned this.
Yeah, okay, it's a complicated object, right? I mean, you have to then check if the thing is coordinate invariant and so on, right? Because if you are saying that some coordinates coincide and the others don't, right? Then that can be changed under coordinate transformation. If all coordinates are coinciding, then yes, that's a well-defined notion, but not otherwise, right? Yeah, so let's try to check that way, right? Two tangent vectors, are they common? Are they parallel, right? So let's suppose that you have a geodesic here and a geodesic here. And you pick 2 points, x1, say x0, x1 and x2. Okay, you have chosen some coordinate system. Then for this geodesic, you have some ni1. Right, that was a tangent vector here. For this geodesic, there is some ni2. Okay. Then you can declare that we will call them parallel if ni1 is some constant times ni2. Okay, in fact, since this constant is not important, we can even just say ni1 equal to ni2. That is one possible definition. Tangents are parallel. So same constant will give this relation for all I. In flat space, it would work, right? In flat space, if you define the tangent vectors to the geodesics and just declare that they are parallel as vector, the two vectors have this relation, then we declare that the lines are parallel. In flat space, if it's true at any pair of points, that's good enough, right? Yeah, because geodesics are straight lines. So here I have already given the fact that these are straight geodesics. In Cartesian coordinates, I mean, yes. Yes.
How are we deciding equal side vector?
Yeah, so that is the problem, right? In flat space, you do this, right? In flat space, you do describe this notion of two different vector spaces, but nevertheless, you declare them to be parallel, right? Aren't the values in? Are in, yes. Yes, so these, as an equation, there's no problem, right? This is what you do in flat space, right? But I think he's asking a more abstract mathematical question, right? If the vector spaces are not the same, right? One is tangent space away at one point, the other one is tangent space at a different point, right? What is the meaning of this? And indeed, that comes to bother us in general Carr space, okay? And the reason is the following. Let's suppose that this is true. We have declared that the two things are parallel, two geodesics are parallel, right? Now, let's see what happens if you change coordinates. So change coordinate system. System to x prime. Then n prime I1 will be del x prime I. Is this clear? I have just used this transformation, okay? Maybe in a reverse direction. Instead of writing n in terms of n prime, I've written n prime in terms of n, right? Just x and x prime exchange. But now you see that these matrices are evaluated, these derivatives are evaluated at different points. One is at x1, one is at x2. Okay? So these are different matrices in general. Okay? So even if this was parallel to this in the sense I have given here, n prime 1 will not be parallel to n prime. Right? Because they are different matrices. Right? If two vectors are parallel, right? If you multiply them by different matrices, then they don't remain parallel. Is that clear? Let's suppose that both vectors are 1, 0. Right? One of them you multiply by the identity matrix, so it remains 1, 0. Right? The other one you multiply by the matrix 0, 1, 1, 0. Right? That converts the 1, 0 to 0, 1. Now they are no longer parallel, right? One is 1, 0, the other one is 0, 1. Okay. So in general, n1 prime I is not equal to some c prime times n2 prime. Okay, so this notion doesn't really work. It's not coordinate independent. Okay. So in flat space, right, now you can go back to flat space. Why does it work in flat space? There also you could do coordinate transformation, right? So in flat space, the reason that it works is because there is a preferred coordinate system. Right? We implicitly assume this, but we never talk about this. There is a preferred Cartesian coordinate system in which this works. And it's in that coordinate system that we use to declare that the two vectors are parallel. Is that clear? Here there is no such preferred coordinate system. Right? So it's not clear what to mean by in which coordinate system you should use to declare them as parallel. Okay. So we'll do the best we can, okay, as in the case of a straight line. Okay. What we'll do is that we'll say, okay, we don't have a preferred coordinate system, okay, but locally in a neighborhood of a point, okay, there is a preferred coordinate system in which gamma is 0. Right? Because that's the coordinate system in which a straight line looks like, geodesic looks like a straight line, right? As best as it can. Okay. So then we'll go to that coordinate system, okay, take a given point, okay, near a given point, we'll take that coordinate system. Okay. And then we'll say that two vectors, two tangent vectors, okay, nearby tangent vectors, and we can go very far because that coordinate system is not valid very far, right? Two nearby tangent vectors, right? Two geodesics which are not intersecting but which are close by. Okay. That between these two, okay, this tangent vector and this tangent vector, okay, we'll declare them to be parallel, okay, if they are parallel in that preferred coordinate system in which gamma is 0. Is that clear? Yeah, that will be our definition of what we mean by parallel. As long as they are close by, right? Yes. So then this procedure will not work, right? So I'm now defining the notion of parallelism between two geodesics which are close by. We can, except that there are very different ways to add them. There are different paths, right? Yeah. And different paths may give different answer. Right? So you have to guard against that. But first you will do it for infinitesimally close geodesics. Okay. And that will give a notion of parallel transport. What is the meaning of a vector here being parallel to a vector there? Okay. And then we'll do exactly what you said, that if you have two far away points, right, we'll draw a curve connecting those 2 points, and along that curve, right, it need not even be geodesic, right? Because these 2 points need not, the curve need not be geodesic. Along the curve, we'll divide into small segments, right? In each segment, we'll define the notion of what we mean by two vectors being parallel, okay? And then we'll translate it. One vector here, we'll translate to another vector there, okay, along that curve. So that way we can decide that two far away points, when are two tangent vectors parallel. But then we'll run into this issue of whether this notion of two tangent vectors being parallel is the same if we choose the different curve. Okay, so this is something that we'll address during the next 2 lectures. Exactly. we can show that if there are two such coordinate systems, right, then the notion of parallelism in one also implies the parallelism in the other. Okay? Because the difference between these two such coordinate systems is really a overall rotation. Okay? And if we make an overall rotation, right, then it changes parallel vectors to parallel vectors. Because I mean, this is probably you can also see from what we have done, right? In order to make the Christoffel symbol 0, we have to adjust certain terms in the transformation of the coordinates, right? And we basically use up all the linear terms, if you remember, right? So you don't have any more linear terms left over. Okay? The quadratic terms don't change the notion of parallelism, right? So the only thing that you can do is that the constant part, right, you can rotate. So x goes to s times x, right? A constant matrix you can rotate by a constant matrix. But that doesn't change the notion of parallelism, right? It's the same matrix, it's x dependent, independent. So this problem is not there, right? Between the nearby points. Not necessarily, because we are not preserving the angle. We are preserving the zero angle, right? Zero angle should go to zero angle, right? So that's what this is saying. Yeah, so for that you don't need orthogonality. For space-time, okay, again, that's the space of geodesics passing through a point, right? But some geodesics may be space-like, some may be time-like, right? But just like here in space, the tangent space is the space of geodesics passing through a point. The same is true for space-time. It's not directly connected to light cone, right? Light cones are in null rays, right? That is the space along which the null rays propagate. But you can also have time-like geodesics or space-like geodesics. Okay? And the light cones will separate them. Why don't they preserve the angle? I think the point is if you make a transformation by some matrix which is not orthonormal, right, then the angle can be changed, right? Because the notion of parallel transport is the angle 0 goes to angle 0. We have not said anything about if they initially they are not parallel, right? Whether the angle should be preserved. That's what we are demanding. We are not demanding that, right? Right now, the way what we are trying to decide if the two vectors are parallel. If they're not parallel, then how much the angle is, right? We are not asking that question. Right? That's why you don't worry about that. Exactly, that will be a stronger constant, right? That will require further condition on the coordinate system. Okay, so we'll continue tomorrow. There is a difference made here. Then the improvement that you are doing, right? Not keeping the same, doing the same. There is a difference. Because these artists, right? You know, always add and declare and sorry. So that doesn't, that you can always do. See, that art is actually the same, that two independent. Q1 and Q. Then you can what with Q1 plus Q2.
This new type of term, right?
So they will by themselves represent a new concept.
By themselves, that's artistic.
Exactly. Suppose you have added some term, sunrise, it's not zero. Then they'll describe some new charge.
I'm asking if this kind of terms show up in like inside the point. Artistically, this is the chart.
See, electromagnetism is little different because when you have gauge symmetry, right? The northern procedure has to be understood different. Because the gauge symmetry is not deep charge. So the global part of the gauge symmetry that corresponds.
For all infinite number of unit times we use masses per sphere.
Yeah, infinite number of trivial currents. But those are no charge.
We have global one corresponds to actual.
Yeah. Other charges will just vanish. Yeah, for any gauge. The global charge is the one that where the gauge transform parameter doesn't vanish. That's what corresponds to a concept. That gauge transformation is different. Let's have a local parameter. You take a local parameter which is non-zero somewhere in the interior and that is that. Corresponding concept charge is identical. Exactly. The only part which survives is the one that corresponds to non-vanishing charge, non-vanishing value of the transformation parameter.
That's why when we get the states with the same transformation are those which actually get
Yes, exactly.
not by your transmission.
And all the other boundary. Exactly.
Okay.
Yeah.
So they're not.
Exactly. That is.
I would say this will to the value for
Global gauge parameter, it always has, so it doesn't have this constraint that it has
So it doesn't have.
like all the other.
Yeah. But what distinguishes between these two cases, where it vanishes and it doesn't. Because when it doesn't vanish and it